So one thing that we can do with a histogram is we can actually draw a histogram with relative frequencies on it. Most of the histograms that we've drawn before on the y-axis, they just had the frequencies. But if you remember back to Module 12, we learned about relative frequencies, joint frequencies, marginal frequencies. You can actually use some of those to draw a histogram. So what we're going to do is take the story that we talked about yesterday, the mass in kilograms of infants or babies that were born, and we're going to use the frequency to create relative frequencies and then draw a histogram using those relative frequencies. So let me kind of walk you through the process. There was one baby born at a mass of 3.2 kilograms. Two babies born at a mass of 3.3 kilograms, and so on and so on. So this table gives us all of our data points. The population that we're talking about is these babies or infants that were born, okay? Now, what I want to do is make a table that instead of just having their frequency, it has their relative frequency. So if you take a look at the one that's done, there's 3.2 kilograms, and there was one baby or one infant at that mass. Now, if you add up how many infants there were, add all that up, there were 20 of them. So that means the relative frequency for that mass is 1/20th. And 1/20th as a decimal is 0.05. So let's try to do 3.3. If you look at 3.3, there were two infants at that mass. That's 2 still out of 20, of course. And that's 0.1. So what we're going to do is fill in the relative frequencies for each of those. So for 3.4, that would be 4/20ths, right? And 4/20ths is 0.2. For 3/5, it ends up being 3.5. It ends up being 0.3. This one is 0.2, 0.1, and 0.05 again for that last mass, okay? They do want us to find the sum of those frequencies. You might actually be able to figure that out without actually adding them. If you think about it, this is 1/20th, 2/20ths, 4/20ths. In the end, that should be all together 20/20ths, right? 20 babies out of 20 babies. 20/20ths is 1. So the sum of all the relative frequencies should always be 1, or 100% of the infants. So hopefully that's kind of logical to you. Now, let's use that information to draw a histogram. We already know how to draw histograms. The only difference is that this histogram is going to use relative frequencies on the y-axis. They were nice enough to give us the intervals and everything. So all we have to do is put in the bars and try to keep them the same width. So this first one, 3.11 to 3.2, that's going to fit this 3.2 category. And we know that the relative frequency was 0.05. So I'll go up to the 0.05. And that's the relative frequency for the first interval. Okay. For the second interval, that was 0.1. So I will fill that one in. And so on. Why don't we continue filling these in? The third one goes to 0.2. Then we go to 0.3. 0.2 again. All right. My guy in the middle there got a little bit thicker than he needs to be, a little bit wider, right? Our goal is really to try to keep them all the same width to the best of our ability. And that is what your histogram using relative frequencies would look like. hopefully that you're noticing that that is nice and symmetric, which means it's a normal distribution. We also know for a fact that it's a normal distribution because if you remember yesterday, we took all the data of the infants. Remember what we did with it? We put it into GeoGebra and we calculated the mean and the median. And you guys told me yesterday, our big walkaway point yesterday was that if the mean and the median are the same, it can be made into a normal distribution. So this normal distribution, we should have expected that to happen based on the fact that yesterday we already knew the mean and the median were the same. Now today, we're going to start talking more about this standard deviation. Follow along with this question. It's a great question. It says, recall that the mean of this data set was 3.5. Remember GeoGebra told us that yesterday? And that the standard deviation was 0.14. Remember what the standard deviation is. It's the average distance that the data points are from that mean. Okay, it explains to you about the spread of the data. They want to know how many standard deviations does a birth mass of 3.2 kilograms differ from the mean. Now I'm going to say that again. It doesn't ask you how far 3.2 is from the mean. It asks you how many standard deviations away from the mean it is. So here's how I'm going to go about this. I'm going to start by finding how far away it actually is from the mean. I know the mean is 3.5. And the birth mass that they're asking me about is 3.2. How far away is that? That would be a subtraction problem, right? If I subtract those, I get 0.3. So the birth weight that they're asking me about is 0.3 away from the mean. But that's not really what the question asks, not yet. The question says, how many standard deviations is that from the mean? Now, a standard deviation is 0.14. So I have to figure out how many 0.14s is that. Now think about add, subtract, multiply, divide. How many 0.14s is that? That's division, right? If I say how many of something can go into it, so I actually want to divide this by 0.14. How many standard deviations can go into that difference? When you do that, you get approximately 2.1. So the answer to my question would be the birth weight of 3.2 kilograms is approximately 2.1 standard deviations from the mean. It's not how far it is from the mean, it's how many of those standard deviations away it is. Now, the difficulty in understanding this problem, sometimes kids get hung up on the division. Like they don't get why I'm dividing there. Sometimes when you're working with harder numbers like decimals, it's a lot easier if you work with simple numbers. So can you move your brains away from the baby example for a second? Let me just show you a really simple example. Let's say I have a bunch of data and I find that the mean is 15. And then I calculate the standard deviation and it's 5. Here's what I know about that data. I know that it's pretty tightly packed. It's pretty tightly grouped. It's not very spread out because the average distance that the data points are from 15 is only 5. That means most of my data falls between 5 below the mean and 5 above, right? Like on average, a lot of the information will fall within 5 below or 5 above. So pretty tightly packed, okay? Now, what if I said to you that there was a data point that was 40 in this grouping, whatever the grouping is? I'm doing the exact same problems but with simpler numbers. If I said to you, how many standard deviations is 40 from the mean? The mean's 15. How far is 40 away? That's what, 25 away? But the standard deviation is 5. So if it's 25 away, and I want to know how many standard deviations that is, it's 5 standard deviations away, right? That's exactly what I did here. I found out how far away it was, and then I determined how many standard deviations away it was. This is going to be really important when we start doing some predicting, okay? Once we start looking at percentages and making predictions and estimates, this is going to be very useful information, okay? Let's take a look at number 4. It says, identify the interval of values that are within 1 standard deviation of the mean and use the frequency table to determine what % of the values in that set are in this interval. That is a lot of words, right? So let me break it apart for you. Identify the interval of values that are within 1 standard deviation of the mean. So here's what I'm going to do. The mean is 3.5. Write this down with me. The mean's 3.5. I know that 1 standard deviation away, a standard deviation is 0.14. So 3.5 plus 0.14 is 3.64. Now, if I go 1 standard deviation below, 3.5 minus 0.14 is 3.36. So when the question says, identify the interval of values that are within 1 standard deviation, that's my range, from 3.36 to 3.64. Everything in between those are 1 standard deviation from the mean. That's the first part of the question. The second part says use the frequency table to determine what % of the values in the set are in this interval. So what % are in that interval? So let's go back up to the top here. Okay. And look at this. Now we're talking about 3.36 to 3.64. Okay. These, for sure, all fall within that category. These, for sure, all fall within that category. And these, for sure, all fall within that category. Right? How many babies is that all together? 4, 6, 4, that's 14 babies all together. So when they say what %, I'm going to go back down here and say, well, it's 14 out of 20, right? 14/20 is 70% of the babies. So 70% of the babies fell within 1 standard deviation of the mean. I want you guys to do this next question. It's almost exactly the same, but instead of the interval of values that are within 1 standard deviation, now they want to know within 2. Okay, so if I'm 2 standard deviations below, that means that I am 0.28 below. That would be 3.22 and above that'd be 3.78. So my interval is between 3.22 and 3.78. If I go back up here, 3.22 to 3.78, we know for sure that everything in this category fits in there, right? Do you guys understand why this one does not fit in there? Like, what if this baby weighed 3.2 exactly? Would that be between these two? No. So because we can't be sure about this baby, we can't include it. This would definitely be in, and in, right? So out of the 20, that is 18. 18/20ths is 90%. So 90% of the infants were within 2 standard deviations. Now, what does this have to do with making predictions and probability estimates, right? That's our learning target, is to make those predictions today. Here's where they come in. We're going to look at something right now called a normal curve. Okay, this is a normal distribution. And we're going to look at the percentages that get assigned to that distribution. So here's what this information is. In a normal distribution, we know that normal distributions are bell-shaped and then they kind of have the tails on the ends. These are the perfect examples of normal distributions. But we also have to understand that there are certain percentages that are assigned to it. This sheet really talks it out well, whereas the other one shows it well. It says a normal curve has the following properties. 68% of the data fall within 1 standard deviation of the mean. 95% of the data fall within 2 standard deviations of the mean. And 99.7% of the data fall within 3 standard deviations of the mean. By the way, if you look at the babies we just talked about, is that kind of what we found? What percent did we find were within 1 standard deviation? Remember, it was 70? Approximately, though. So that's pretty close. What percent did we find that were within 2 standard deviations? I think we got 90, but that's approximate. It's an estimate. So that was also pretty close. Now, how is this information shown in here? Let me talk you through this. 1 standard deviation is from here to here. Okay, the line in the middle is the mean. So what percent fall within that range? 68, right? 2 standard deviations would be here. 95% fall there. And then 3 standard deviations, 99.7% fall there. Now, here's an even further breakdown. If you look at 1 standard deviation, if 68% fall in that range, how much would be on each side of the mean? 34 and 34, right? So if this is 2 standard deviations apart, 2 standard deviations from the mean, and all together, that has to be 95%. 68% was in the middle. So to get to the 95, there's got to be 13.5 on the left and 13.5 on the right. Now, to get out to the 3rd standard deviation, you'd have to add another 2.35% on each side. And then this 0.15%, that's the percent that would fall above or below 3 standard deviations. So let's put an actual story to this. It'll make more sense when you see it in a story. Getting rid of the babies for a minute, moving on to pennies. the masses in grams of pennies minted in the United States after 1982 are normally distributed with a mean of 2.5 grams and a standard deviation of 0.2 grams. Find the percent of pennies that have a mass between 2.46 grams and 2.54 grams. Here's our predicting that we've been waiting for, right? Part of our learning target. Let me put this all in clear numbers for you. The mean is 2.5 grams. Write this down. The standard deviation is 0.02 grams. They want to know what percent will fall between 2.46 grams and 2.54 grams. That's the question. All boiled down to easy numbers. If the mean is 2.5, one standard deviation above, 0.02 above, would be 2.52, right? Another standard deviation above would be 2.54. Now if I go below one standard deviation, that's 2.48. If I go below another standard deviation, that's 2.46. So if they want to know what percent land between here and here, those are each 2 standard deviations away. Everybody agree? 2 standard deviations away. So you go back to your chart and you take a look. 2 standard deviations away, what percent should fall, if it's a normal distribution, between those 2 numbers? It should be 95%. Now that's an estimate, it's a prediction. If you really weighed 100 pennies, would 95 of them weigh between 2.46 grams and 2.54 grams? Pretty close. It might not be exact, because remember this is an estimate, but it should be pretty close to 95% of them. Okay. Now how about this question? Same scenario, but now I want to know what percent are going to weigh above, what percent are going to weigh above 2.52 grams? So 2.52 is 1 standard deviation above. So if I go to this chart, that puts it here. Now the question is, how many would weigh more than that? So the 13.5 would weigh more than that. The 2.35% would weigh more than that. And the 0.15% would weigh more than that. If you add those 3 percentages together, 16% would weigh more than that. So if you weighed 100 pennies, 16 of them should weigh more than 2.52.